Hello, and welcome to my presentation on my honors capstone project. My name is Travis Gerlich. I'm a graduating senior with a major in computer science and engineering and a minor in mathematics. Today, I will be talking about the MDP project that I worked on over the last year, the Robotic 3D Tetris project sponsored by Comau. This presentation will provide a full overview of as much of the project as I am able to share. I'll start by describing the problem we set out to solve, followed by how we solved it. Next, I'll talk about how successful our system was, before ending with some next steps another team picking up our project could pursue. With that, let's get started. The problem that Comau presented to us in January was to create a software and hardware system that measures incoming items and determines the best place to put them within a given container. These items come one at a time, so we don't know what will be coming next. This means we can't find a truly optimal way to pack the container. We just have to do the best we can with each item as it comes in. Once the placement for an item is determined, our system is to relay this information to a robotic system provided by Comau that would handle actually placing the item in the container. We had four main goals for this project. The first goal was to measure the dimensions of incoming items within a 2.5% margin of error. The second goal was to complete a full cycle of the system, including the item being placed in the staging area, the robot packing the item into the container, and the system being ready for the next item within 10 seconds. The third goal was to fill at least 85% of the container before no more items can be placed within it, and our fourth and final goal was to include an easy-to-use graphical interface, or GUI for short, that would handle all of the manual interaction with the system and visualize the status of the system. To measure the items, our system uses a process called segmentation. In this process, it uses a pair of depth cameras, special cameras that can measure the distance from the cameras to various points in the camera's view, to generate a point cloud of the item. This point cloud contains a number of three-dimensional points which, after some filtering to remove the background points, are all on the surface of the item. Using these points, we can create a bounding box for the item. This bounding box is oriented to match the orientation of the item and is the smallest box that will hold all of the points, so the dimensions of the box are roughly equal to the dimensions of the item. Once the item has been measured, we can attempt to pack it into the container. To do this, we use a modified version of an algorithm known as the online bin packing heuristic. This algorithm tracks the empty space within the container using empty maximal spaces, or EMSs. Items are placed based on their bottom back left corners, so these EMSs effectively track where new items can be placed and how big an item placed at that location can be. These EMSs are stored in order of decreasing priority based on their locations within the container. When new dimensions are received from the segmentation algorithm, the bin packing algorithm checks each EMS in order to see if the item will fit in it, and, if so, how it must be rotated to fit in that location. Once a location where the item will fit is found, the item is placed within the container. The EMSs are then updated to match the new state of the container, with new EMSs added to account for the new item, and the old EMSs updated as needed so they only contain empty space. This process repeats until the system gets an item that doesn't fit in any of the EMSs, at which point the program stops. The GUI used to visualize the system, as shown on the previous slide, consists of two separate programs: a Java-based bin packing visualizer, seen on the left side of the slide, and a C++-based data and parameter interface, seen on the right side of the slide. The bin packing visualization allows for both mouse and keyboard controls to view the container from different angles, while the data and parameters interface is able to send the dimensions of the container to the bin packing algorithm and receive data on incoming and packed items from both the segmentation and bin packing programs. We encountered a number of challenges when developing our GUI. Our initial GUI concepts were web-based, that is, we intended to make them in HTML, CSS, and JavaScript. Unfortunately, the bin packing visualizer had to be moved to a separate program due to issues with rendering the container and placed items, while the data and parameters interface had been moved to the terminal due to issues communicating with the other programs in the system. While it would have been better to have a single program for the GUI, changing our approach allowed us to get all of the GUI's features working within the time that we had. As you may have noticed, each of the last three slides cover separate algorithms and processes. To get all of these processes connected and allow them to communicate with one another, we use the TCPIP communication protocol. In this protocol, when two programs want to communicate, one acts as the server, while the other acts as the client. The server opens a socket on a certain network port and begins accepting incoming connections to that socket. The client can then connect to the socket, and the two programs can use the socket for two-way communication. This slide includes the outputs from two sample programs that use this protocol. The process on the left is the server, while the one on the right is the client. The server creates the socket, which the client then connects to. The client then generates a set of values, which it sends to the server over the socket. Upon receiving this data, the server sends an acknowledgement to the client, which the client uses to know when it can send the next set of data. Ultimately, the components of our system were successful in performing their tasks, even if some of them fell a little short of our initial goals. Our segmentation algorithm met its goal of measuring items within a 2.5% margin of error, often getting within half a centimeter to the actual dimensions. Our bin packing algorithm is able to fill 75% of a given container in the best case. While this falls short of our original goal of 85%, we are able to continuously improve our algorithm and are happy with the results we were able to obtain. Our GUI accurately visualizes our system, and the two components are easy to use. That said, the data and parameters interface can be a bit difficult to read at times due to its nature as a terminal-based program. While the pandemic prevented us from testing our system in an actual work environment, and thus getting an accurate measurement of the system's cycle time, it was able to simulate the packing of actual items in a lab environment. Since our target cycle time for the whole system, including the robot, was 10 seconds, we set a goal of 4 seconds for a cycle time without the robot, which our system is able to meet. On this slide, you can see some of the different aspects of our system working together, though I apologize for needing to hide part of the image. I'm not allowed to show what our system is actually packing. Visible is the computer running the segmentation algorithm. In a real environment, this would be a Raspberry Pi. One of the two depth cameras that are responsible for creating the point cloud of the object, and a view of the bin packing visualizer showing the previously placed items. While we were able to make a lot of great progress on this project, there are some ways that each aspect of our project could be improved with more time. The biggest and most complex change that could be made to our system, and something I feel would be interesting to look into given more time, would be making the modeling and simulation more realistic. Currently, our system assumes that incoming items are rectangular prisms. While this isn't necessarily inaccurate, the items commonly deviate from a perfect prism in ways that might impact how they would be packed into the container. Additionally, our system assumes every item is perfectly rigid, which is generally not the case. Updating our models and simulation to allow for these additional properties would help improve our algorithm and avoid minor errors caused by our simplifying assumptions, such as some items slightly floating above others, as you can see on this slide. For our bin packing algorithm specifically, we could update how items are placed to minimize the amount of space left between items. As you can see, even our best case packing leaves a good amount of space between the items that we could certainly cut down on. More accurate simulations, as mentioned on the previous slide, could potentially help with this process. Finally, as has been mentioned previously, the two aspects of our GUI could be combined into a single program to improve ease of use and readability. This splitting of the GUI into two separate programs came about because we started development of the GUI a bit later in the project, and thus ran out of time to fix the issues without changing our approach. If given the opportunity to do this project again, I would start development on the GUI earlier, so we would have more time to work through some of the issues that we encountered. This would enable us to potentially resolve the rendering and communication issues we experienced during development of the web-based version of the GUI. All in all, while there are certainly areas where our system could be improved, I'm very happy with what we were able to accomplish over the last year. We met or got close to meeting all of our established goals and learned a number of technical and non-technical skills along the way. I would like to thank my fellow team members Joey Berman, Shannon Lau, Hannah Moon, Arjun Raman, and Jonathan Wong for all of the hard work they put into this project, our faculty mentor Vineet Kamat for helping us navigate this project, and our sponsor mentor Joshua Graff for his advice, support, and enthusiasm over the past year. Finally, thank you for taking time to watch this presentation and learn a bit more about our work. If you have any questions about our project, feel free to leave them in the comments below this video.